All right, I think we have most of the students. Let's get started. Today we'll talk more about pipeline processor. This is going to be the last lecture on pipelining. We'll talk about some of these additional scenarios, some data forwarding, and also we'll look at this control unit. We'll try to understand how we actually detect this forwarding and also detect hazard dynamically. Before that, I have a couple scheduling issues that I want to mention. I also need to do a poll on item pool. First, pre-lab 4A is due tonight. Okay, we cannot make it due tomorrow because this is tomorrow is Wellness Day. Also, we cannot make it due on Monday, right? Same reason. And pre-lab 4B will be due, right? And also lab 4A will be due next week. So this is the only day, right? For this only possibility for setting the deadline. Okay. But we are just ahead. Just want to give you a most likely we'll try to simplify the part B for lab 4 so that you guys have a bit more time to enjoy your Wellness Day. Just stay tuned. We are working on that. So we may release an updated lab handout later today or tomorrow. Okay. So we'll try to do some simplification to reduce some of the tedious part of this lab. Okay, and also as I already mentioned on Piazza, I have to cancel my office hour today. I have a schedule conflict. Also, because of the break, right? There's no TA office hour tomorrow. But we have added the extra hours today, right? From 3 and 9 p.m. Okay, and also one more thing, I may have to reschedule the lecture next Thursday, which is actually not lecture 20. I need to correct this. This is actually lecture 21 because today's lecture is lecture 19. This is a typo. Lecture 21 next Thursday, because I'm getting my second vaccine shot next Wednesday. Based on what I heard from some of my colleagues and so from many of you, there's really no guarantee that I'll be fit enough to teach the next day. So I may have to come up with this plan B. This is where I really need your help, right, to help me decide the alternative slot. Can you guys all go to item pool? Hope you are seeing the screen. Okay, I need you guys to vote. So this is again, this is lecture 21, right? Not lecture 20, which is supposed to happen on April 24th. Right? Okay, thanks, Sebastian, for posting link. But please be flexible. Please mark all the choices that you can make, all the slots that you can make. Unfortunately, I have to schedule it over the weekend. And also I try to make sure that since we have some remote students from Asia dialing in, I want to make sure that the alternate slot is close enough to the regular slot. Okay, so that's why we are doing 11 a.m. or 1 p.m. either on Saturday or Sunday. Okay. And of course, these lectures will be recorded, right? So in case you have to miss it, please watch the recorded video. All right, let's see. Okay, so it looks like option D has most of the votes. Okay, so most likely I'll go with either option D or option C. I'm gonna announce that next week. I'm gonna let you know if I indeed don't feel too well, right, to teach. I'll let you know, and then also let you know about the alternative slot. All right, thanks. Since we are on item pool, let me ask you guys one more question. Okay, just want to refresh your mind about what we covered last week, right? We have been talking about pipelining, data forwarding, right? We have covered quite a few different things, right? Bypassing, control hazard, right? CPI, delay slot. Mark, which one of these statements are true? this is a multi-choice question. This is going to be really helpful for you guys to refresh your mind. And also some of the things will be discovered again in today's lecture. Right. First, data forwarding is also called bypassing. Second one, branch can only introduce control hazard. Right. Third one, we see the forwarding, we can get an ideal pipeline, which is a CPI of 1. Last one, delay slot is defined as part of the instruction set architecture or ISA. Right. I'll give you guys maybe 10 more seconds. Again, this is a multi-choice question. Okay. Let's see whether there's anything on the chat window. All right. I think most of you have entered your answer, right? Okay, let's see which ones are the correct and true things. Right. Okay, very good, right? I think most of you mark A and D, right? Some of you did mark C, right, which is a tricky one. Okay, let's just go over one by one, right? First, indeed, right, data forwarding is also called bypassing. So these two terms can be used interchangeably. Second one, branch instruction indeed can introduce control hazards, right? So that's where we may not know, right? When during the pipeline, when the execution, we may not know whether a branch is going to be taken or not. That's where if certain instructions are already in the pipeline, which has to be thrown away later, that's where we have this so-called control hazard. Right? But what else can branch instruction introduce other than control hazard? Data hazard, right? Very good, because branch instruction also need to read some register value, right, to determine whether we need to take a branch or not. Third one, with data forwarding, the pipeline can achieve the ideal CPI. Okay, this is actually not true because there are still cases where we have to insert bubbles, and we're going to look at those cases. I think we briefly touched on some of those last time, but we'll see a lot more of those. But even with data forwarding, we still have to stall the pipeline. Okay, last one is kind of a simple, right? Simple one. So this is where let me switch back to my second screen. We have been talking about this delay slot, right? At the end of last lecture, delay slot is indeed defined as part of the instruction set architecture. Okay, very good. Looks like most of you still remember, right, what we talked about last time. Right. Again, it's going to be lecture 21. I'm going to fix this. Let's see. All right. Okay. Somehow my screen is not moving. Okay, now it's moving. Okay, we just talked about branch delay slot, right? And this is the quiz that you guys did last time. I asked you guys to find one instruction to move, right, to this delay slot to replace no. This is the delay slot. Right? With a branch delay slot defined, this instruction is going to be executed unconditionally, right? The microprocessor, the hardware, is not going to bother to check whether there's a hazard or not. Compiler is supposed to guarantee the correctness of the program in this case. Okay, I think most of you marked this instruction, right? And indeed, right, this is an independent instruction, okay, which can be moved into the delay slot. But let me make one more tweak, okay, to this instruction sequence. What if I change this register index from R6 to R7? Can we still make the move? Can we still move at I? No, right? Why not? What's the issue here, right? indeed, there's a dependency, right, between addi and sub. But if we move addi is still before sub, right? What's wrong? What is the problem? Anyone want to chime in? Right. So now there's indeed this data dependency, right, between these two instructions. Okay, very good. Steve is saying that addi, if you move addi, right, if you actually move addi over here, addi can be skipped, right? If branch is it true? Can addi be skipped? Can addi be skipped? Is it a yes or no? Okay, so can we move? Let me ask you this question again, right? Can we move addi or not in this case? First, if we move addi over there, right, to the branch delay slot, are we skipping addi or not? No, right? We are not skipping addi because this is the delay slot. It's going to be executed regardless. So is there any other issue? Can we move addi in this case? Any second thought? Yes. Okay. Anyone still think this is no? Okay. Any questions? So Alma, what are you asking? What's before?
Oh, my question is like for add, immediate, and sub, if R7 is what's being written to for both, then how come, like what, can you just describe what the data dependency is again between addi and sub?
Oh, so I was just saying that if we change, right, first, I think we all agree that in this original sequence, right, we can move addi, right? There's no data dependency. But what if we change this instruction, sub instruction, right, to write to R7? I should not have changed this one. There's no, sorry. I actually wanted to change this guy, R7. Sorry for confusing you guys. Okay, I meant to change this one. So then there's this dependency, right? Yeah, good question. I did not know this. I changed the wrong registry index. Is it clear now?
Oh, yeah, now it's clear. Thank you.
Okay, right. Something to think about, right? You know, if indeed there's a dependency, if you still move it, right? Is it still legal move or not? Okay. All right. But one thing is, you know, if you actually move it to the delay stop, it is going to be executed unconditionally. All right, so let's talk about this control unit, right? We have been mainly focusing on the data paths. So far, we have been mainly focusing on these black lines, right, which are the data signals. In today's lecture, we also look at this the blue lines, right? This how we actually generate these control signals using this pipeline control unit or CU. Okay. Many of the control signals should look very familiar to you guys, right? Since you guys just took Prim 2, which is something that we're going to grade, but most likely slightly later, since because of the wellness day, right? The TAs also need to take a break. We will let you know. Okay, so with this which is a branch human sex, right? Sorry. Okay, so I was talking about this control units and also the control signals, right? You know, some of these are already familiar to you guys, right? MB, right? MW, and these are the function select, right? Okay, so let's see how we actually generate this. First, these are the requirements. We do want to generate the right control signals for each state. For the instruction fetch, we want to generate something called PCJ. We look at it. Again, this is where we control the jump, right? Where we take the branch or not. And then we have something called MB, right? F is really the function select. So these are something that you guys have practiced over and over again, right? Including prim2, MW, MD, LD, right? So these are the things that we're going to generate correctly at different stages. And today we're going to introduce something new. So we also need to detect these forwarding conditions, right? And also generate the associated mux control. With this forwarding, we are introducing additional muxes. And we will also talk about how to detect hazards. Even with the forwarding, like I mentioned, we may still have hazards. So that's where we may have to introduce these pipeline bubbles. We have to stall the pipeline in certain cases. Also, one important assumption from this lecture, so we assume that there's no low delay stop defined in the ISA. Going forward in homework and also in the final exam, we'll make it clear whether there's a branch delay start or a low delay start. It's going to be specified as part of the problem. Okay. And there's a branch delay start. Okay. This assumption for today's lecture. What does that mean? Is there any control hazard or not if we do have a branch delay stop in our 2300 microprocessor? Do we still need to deal with control hazard? Yes or no? Anyone? Again, this assumption, right? You assume that there is a branch delay start defined. Right, Emily, you're right. Right. No, since we are deciding whether we take the branch or not in the second stage, the ID stage, and we introduce one branch delay start. That means the instruction in the IF stage, right, which succeed the branch instruction will be always executed. So that's where we simplify our scenario quite a bit. We don't have to handle the branch hazard. In practice, in the modern microprocessors, we actually have a more advanced branching scheme. We actually try to do branch prediction to further improve the performance, because it's not like we can always find something to fill into that delay stop. It's not something that we are going to cover in this course. This is going to be something that's going to be covered in a more advanced computer architecture course. Okay. All right. So these are the things, right, that we need to take care of. So first, for the the PC control, right? Once we know whether we need to take the branch or not, that's where we want to generate this signal called TCJ, right over here. Really, this signal, right? This line, the blue line is supposed to connect to this line over here, right? So these are the same signal. This one determines whether we take the default increment, right? PC increment, or we take the branch, right? The signal. Okay. Next, this is where, right, we're going to be propagating, we're going to be generating all these control signals, right? And all these control signals will be propagated through the pipeline, right, stage by stage. And they're going to be consumed. Some of those will be consumed in certain stages. For example, MB, right? This is basically where we select the second operand, right? Whether we take data B or the immediate. MB will be consumed in this EX stage. And F really means this. This tells what ALU tells give the ALU the command, right? This is the opcode for the ALU, the function select. Right, and next stage, this is MM stage. That's where we generate MW and MD. Okay. Again, this is already generated, but this is actually propagated. Let me be more precise. It's already generated in the ID stage, right? The CU parse instruction, the decoder parse instruction, and then send the additional input, right, to the CU, and CU generate all this the right control word, and all of this will be propagated and consumed at certain stages. Over here, MW and MD will be consumed here. Eventually, LD, right? LD is the write enable for the register file. LD will be consumed here in the write back stage. Okay, so these are pretty straightforward, I suppose. Okay, any questions about this one? Right, if not, let's also look at forwarding. This is more interesting. We have been looking at forwarding, right, quite a bit since the last lecture, right? With forwarding, we are introducing this additional muxes, right? See here. Initially, we only need to grab the data A and data B from RF. Now, in some cases, we also need to, we actually want to take the ones forwarded from the print instructions, right? So this could be forwarded from the mem stage, right? So this is where we take this pass, right? We have this feedback pass, or some matter can be forwarded all the way from the write back stage. That's where we take this pass. Okay, that's where we have these muxes, right, for the ID, and in some cases we also forward to EX. That's where we also introduce additional muxes here, right? Okay, and but we need to detect, right? When do we enable or activate this sort of a backward pass, right? This sort of a forwarding pass like this. So when do we exactly enable this? What do we check? Okay, what information do we need? This is where we need to introduce this so-called forwarding unit. Okay. This is also sort of a control unit. And this control unit takes in these many inputs. Even actually this one is a partial. I'm making this clear here. This is actually a partial design, right? Because there's just no way that I can fit squeeze all these different signals into one page, into one slide. But these ones are the important inputs, right, to the forwarding units. Right. So first, we actually need to know what kind of instructions that we have in each stage. This one means, you look at this one, mems dot R type means that whether we have an R type instruction in the memory stage. So basically, we are trying to propagate the information, the important information of the instruction, okay, through the pipeline. And in each stage, we know what kind of instruction we are dealing with. Is it R type? Okay, is it I type? Is it load or branch and such? We also want to know for the instruction in the current mem stage. Let's say the instruction that's being executed in the mem stage, what is the destination register, right? DR is the destination register. Same thing, right? We actually want to know what's in WB stage and what's in ID stage and what's in EX stage. Does it make sense? We actually need to know this kind of information, right, before we can decide whether we need to do forward or not. For example, if we want to enable this pass, right, from mem to EX, this one, what do we check? Any guesses? What information do we need? What do we actually check in the forwarding unit? Where do those inputs come from? Is it a question or is it the answer, Amanda? This is a question? Right, so first, this one, right, in case you are still a little bit confused, right, these ones are the information of bits that we need to, we have the information here, right? After decoding the instruction, we know exactly what kind of instruction, is it I type or R type, and DR, right, SA, SB, what kind of instruction we are dealing with. We know exactly what are the fields, right, in this instruction. And we need to propagate this information through the pipeline. Okay? Basically, per stage, we have the information, we have access to this information, whether this is the R type or what is the destination register, what is the source register for the corresponding instruction in this current stage. Okay, coming back to my question again. So you want to check whether we have a forwarding or not, right? We need to enable this forwarding or not. We need to check what kind of instruction we are dealing with, right? So in the mem stage and the EX stage. And we need to check whether there's a data dependency or not. Is it clear? How do we check that? Okay, how do we check that? What do we use if there's a data dependency? We want to use mem.dr, right? We want to see whether mem.dr matches which one. So we are looking at this one, right? This is really data A. matches this guy or not. It's clear? If there's a match, if the instruction in the memory stage is supposed to, let's say this one equals R1, right? This one also equals R1, then we have a potential data hazard, right? That's where we need to forward. Okay. Right. So these are basically you can imagine that all of this information, I mean, a good question, right? So basically these are all of these are binary values, right? You can imagine that all of the information are stored in this pipeline register. Okay. And they are being forwarded, okay, from one stage to the next stage. Any more questions? The assumption here is that, in each stage, we know exactly what kind of instruction we are dealing with, what are the source registers and which register we are writing to. If it's if indeed we need to write to a register. With this information, we can detect the data forwarding, right? Okay. All right, so let's just try to make it clear, make it more specific. Let's look at this R-type to R-type forwarding again. This is where we have 3 different scenarios, right? Okay, if you look at this one, later on, I need to make sure that you guys can name make sure that you guys can name the forwarding path. This is from mem, right, to EX. This is how we name the forwarding path. This one is mem to EX. With this one, we want to check whether there's a match or not. Right? We compare the destination register index in the memory stage with the source register index. Right? We really need to compare with both of them, right? Either both are SA or SBE. If either one has a match, then we need to enable the forwarding path, right? Because there's a data dependency. All right, this one, the second path, this is where we forward from WB to EX. Right? And here's the condition. Again, this part is not that surprising, right? We also need to check whether there's a dependency or not. Okay. Once again, these are the information being held in the pipeline register. So which pipeline register do you think we are using? Like, where do you think this one is stored? This information is stored, this one. Any suggestions? This one. Where is this information stored? In which pipeline register? Any suggestion? Mem WB, right? Slash W, very good. Over here, right? Page 3. Mem slash WB. Okay, so this is where we store the decoded information of the instruction. Okay, and we need to check, right, whether there's a match or not. If there is, we may need to forward. But here's a second condition. So this is something that we're going to discuss pretty soon. And this one is kind of interesting. Right? We also need to make sure that there's no forwarding from mem to EX. Okay. If there's no forwarding from mem to EX, and there's a forwarding from WB to EX, then we enable this path. Okay, Amanda is asking, where is EX stored? Okay, what do you guys think? Where is this information stored? EX.SA. Which pipeline register? Oh, here, right? Sorry. Oh, here. ID slash EX. That's where we can find EX.SA, EX.SB. Essentially, we are just propagating, right, this information, DR, right? We basically pack them together, right, into many bits, right? SA, SB. Just imagine that we have a bundle of bits. And this bundle of bits is being propagated through this pipeline register. Okay, why not? I think I was asking you guys about. Oh, did I first for this where from this register, that's where we find wb.dr, right? Okay, we basically look at the register on the left because this is something that we are reading from the current stage, right? You want to find mw, not mw. You want to find mem.dr. We look for ex/mem. Does it make sense? Right. So per stage, we just look at the pattern register on the left because that's something that we are reading from. Okay, because we are writing to the register on the right. Right. Any more questions? Okay, and the third pass, this one is where we check, right, whether there's again a match. Okay. For this information, let me just make sure that you guys is following, right? Where do we find this one? Where do we find this one? From which pipeline register? Anyone? Very good. IS/ID. Okay. All right. These are the three forwarding passes, right? For R type to R type. We only need this three different passes for R to R forwarding. But why do we have this, right? Why do we have this kind of check, right? For a second pass. Let's see. Let's look at a different example. Okay, so see here the instruction sequence slightly different. We still have this data dependency, right, between add and or. That's where we are doing the forwarding. Okay. Notice that or is also writing to R1. So my next question is, do we want to enable the forwarding pass from here, from WB to EX? Do we want to forward from here to here? No, bad idea, right? Because R1 is already updating, it's already being updated by or, by the second instruction or. But if you look at this forwarding pass, right, indeed we have a match here, right? Indeed so if you look at, just want to be clear, right? You look at this dash line, right? This dashed line here, you check this pass and come back to these conditions. This condition is true, right? We do have a match, but this may not be the path that we want to take. If there's another active path, that's another active forwarding that's going on from mem to ex. Okay, that's why we are adding this second condition. So we really don't want to take this path, right? We don't want to do this forwarding. We don't want to do this forwarding. We really want to enable this forwarding. Okay. So instead, we want to use a more recent forwarding, right? This is a more recent one, more recent R1. We will use this path instead. And of course, there are other paths that we want to enable. Okay. All right. So just want to recap. This is basically how we can build the forwarding logic inside is a forwarding unit for R-type to R-type forwarding. All you guys need to write is this, right, in your Verilog. You want to build of course, we're not asking you guys to build a pipeline microprocessor in your lab. Okay. But if you have to build one, these are the things that you have to check, and that's it. Okay. Right. So basically, to enable this pass, we should check this, right? To enable this pass, we check these two conditions. And the last one, we check this guy. All right, any questions? Okay, good. So this R type to R type, right? What about R type to branch? This is not something that we discussed last time. We do have a dependency here, right? If you look at this instruction sequence, first instruction writing R1, this guy is reading from R1, BGEZ. It's basically checking whether R1 is greater or equal to 0. How do we forward? We do need to forward, right? From which stage to which stage? Can you guys propose a forwarding path? Anyone? It's produced, right? So it's already available here, right? In cycle 4, this R1, we want to do this forwarding, right? Where is R1 used for the branch instruction? Which stage? Where is it used? Anyone? Is it used in the ALU? So let me go back to this slide. Where do we actually do the branch? Remember that now we have a single delay slot, right? That means we want to resolve the branch condition in the second stage, in the ID stage, right? So that's where, yeah, very good, Sebastian, also Carol and Stephen, right? So we do want to resolve the branch condition over here in ID stage. Otherwise, we need 2 delay slots. That's just too many. And we don't need a full-blown ALU. Instead, we just need to add a comparator like this. So we can make the comparison, right? Since in our 2300 RSA, we only have a few branch instructions, like 4. This is good enough, right? So basically for branch, we are reading from the registers in the second stage, in the ID stage. Is it clear? Okay, so with this in mind, let's come back to that example. One more slide. Where do we forward? Or to what? From which stage to which stage? Any proposals? Very good, Jacob. Like this, right? We do mem to ID because R1, right? R1 is already available here, okay, in cycle 4, and we need to use it over here, right, to make the branch decision. So that's where we do this kind of forwarding. This is where we have right, R1 R type instruction, which is like sort of 2 cycles apart, right? From the branch, there are other conditions as well, other scenarios as well. You know, there are 3 cycles apart. You guys should convince yourself there are other forwarding processes that we may have to add or enable. For example, we may need to have this WB to ID, okay, just to resolve the branch, right, to enable the branching, right, calculation. Okay, if this is still not too clear, right? So let's see. Let's look at this is just the abstract view, right? Let's look at the physical view. This is the actual hardware. This is the path, the yellow path is the one that we just talked about. Right? We are looking at this MEM, right? We're coming from the memory stage. This is a backward path, right, in the physical hardware to the ID stage, right? Over here we assume that this addition is already in the MEM stage, right? And the branch is currently in the ID stage. We want to enable this forwarding, right? So that's where we don't want the branch to read out the old R1 from the register file from RF. Instead, we want to read the new one, and we want to take this path. Okay, any questions?